Hi guys, this is our sample problem for 8.4. It's a little bit harder than the example in the textbook, so I wanted to make sure I did one that was a bit more challenging for you so you can see all of the techniques that you're going to need to use to do this. So we are given two functions here, f of x, which is a cubic, g of x, which is a quadratic, and the question is find when f of x is greater than g of x and when f of x is less than g of x. So, excuse me, we're going to do it both algebraically and graphically. And so with two different methods, with the method of finding when one is graphing both and analyzing how the graphs relate to each other, and also graphing the difference function. So let's start with graphing both functions, and then we'll analyze that graph. So in order to graph these two functions, we can do a few things. We should use our prior knowledge of cubics and quadratics. That will help us. And we're actually going to do more of a sketch than a graph. But one thing that we can do to sort of anchor the functions to see exactly how they relate to each other is find the points of intersection. So that's what we're going to do first. So we're going to make the functions equal to each other and solve for the points of intersection. And that will give us sort of a focal point for where we want to be seeing the graphs. Because in order to determine where f of x is greater than g of x, we'll want to know physically where the graph of f of x is above the graph of g of x, and vice versa for f of x less than g of x. So let's start off by finding the points of intersection here. So I've equated them, and I'm going to take everything over to the left side, simplify it. And when I do that, I'm going to skip those steps. You can stop, pause the video and do them on your own if you want, just to make sure you remember how to do them. But basically, we just take everything to the left side and collect like terms. It comes out to this. And so lucky for us, this is fairly easy to factor because we can first just take out the common factor of x, and then we are left with a quadratic in the brackets, which again, lucky for us, is fairly easy to factor. It comes to x times x plus 10 times x minus 1 equals 0, and then our roots are x equals 0, negative 10, and 1. So just before we move on to find the y values that go with those, what would we do if we ended up with a constant term over here, for example? So then it wouldn't be as easy to just factor out the x and then factor a quadratic. We would have to factor cubic, so we would have to use factor theorem. Another complication that could occur is that we do end up with a quadratic in here, but it's not factorable. So what would we do then? We would have to use the quadratic formula to get the roots. So one way or another, we need the roots of this equation, right? Of this polynomial equation. And so you got to take yourself way back to chapter 2 for that. Okay, so once we have our roots here, we should put them back into either f of x or g of x to get the y values that go with them. And I've already done that, so I'm just going to write them here. 0 goes with negative 12. Negative 10 goes with negative 102. And 1 goes with, negative 14. So those are our points of intersection of the two functions. Now, what we would want to do next is make a sketch of these functions. So I'm just going to skip ahead a minute here. I made my graph already because it's really tricky to do it on this tablet because it's kind of slippery. And so it took me a while to make this sketch. It shouldn't take you as long on paper. Anyway, how did I do it? So first thing I did is I looked at the cubic. F of x equals x cubed plus 8x squared minus 11x minus 12. And so that's the cubic on the graph here. So I noticed a few things, used my knowledge from chapter 1. It is a cubic, so that tells me what the shape is. It has a positive leading coefficient, and so that tells me that the end behavior is Q1 to Q3 for a cubic with a positive leading coefficient. And then I put my points of intersection on the graph and use those as points on the cubic. So remember, it's a sketch. I don't know exactly how high it's going up here at this point. I don't know exactly how low it's going down there, but it doesn't really matter to the solution of where f of x is greater than g of x. So a sketch will do just fine. I just want to point out, notice that my scales on the x-axis and y-axis are different, which is fine. They don't have to be the same. I went by twos on the x-axis and 10s on the y-axis, because if you go back here and look at your intersection points, the x values are 0, -10, and 1, but the y values go all the way down to -102. So we wouldn't be able to do the same scale on both axes anyway. I just wanted to point that out. Okay, so that's a sketch of the cubic. For the quadratic, g of x equals -x squared minus x minus 12. If you want, you can complete the square and get the vertex, but you don't really need to, because there's really only one way that this quadratic can go through all three of these intersection points, and so I've sketched it in there. And you can see there's a bit of overlap between the two functions in this section here. Okay, so also we know that the quadratic has a negative leading coefficient, and so therefore it opens down. Okay, so looking at this sketch now, we need to find where f of x is greater than g of x. Let me just fix my x over here. Okay, and so f of x is greater than g of x wherever the graph of f of x is above g of x. So I'm just going to take a different color here and shade that in. So between this point of intersection and this point of intersection, f of x is above g of x in this whole interval here. And then in the next interval from here to here, it's below, so we don't include that here. But again, in this, from this point of intersection to infinity, pretty much, f of x is above g of x. Okay, so what is the solution? The solution is that f of x is greater than g of x, and I'm just going to go back to my red color here. When x is an element, let me just clear some space for myself to write this here, sorry. So x is an element of, from this point of intersection, from the leftmost point of intersection to the next one to the right, is the interval -10 to 0, union the interval 1 to infinity. Okay, so notice I have round brackets, not square brackets, because it's greater than, not greater than, or equal to. So that's the solution for f of x greater than g of x. And now we need to do f of x less than g of x. And so, of course, that would just be the interval that remains in between these two intervals, because in that interval, f of x is actually below g of x. And so the solution for that inequality is x is an element of 0 to 1. All right, so that was method 1 where we graph both functions and we observe where one function is above or below the other. The next method, and you would have seen this in the textbook when you went through example 1 on your own, it would be to graph the difference function. So first thing we need to do is actually get the difference function. So we need f of x minus g of x. And so we just take our functions and subtract them. X squared plus 8x, x cubed plus 8x squared minus 11x minus 12 minus, and don't forget to put a bracket here so that you distribute that negative over the entire g of x, otherwise you are not going to get the right answer. And that simplifies to x cubed plus 9x squared minus 10x, which is of course the same thing that we had the first time on the left side of the equation. And then to graph it, so this is now one cubic function that we want to graph, and the easiest way to graph it would be to get the x-intercepts and then use the properties that we know that it's got a positive leading coefficient again. And so it's a cubic with positive leading coefficient, and so the M behavior again is going to be Q1 to Q3. So to get those x-intercepts, we just factor it, and it factors out once again to the same thing it factored out the first time in our first method on the left-hand side of the equation. The only difference is that was equal to 0, this isn't. But to get the x-intercepts, we want to make it equal to 0 anyway. So we end up with the same roots as before, 0, negative 10, and 1. And so those are our x-intercepts. And we make a quick sketch of this. So again, I'm going to do 2's on the x-axis. And so 0, 1, and negative 10 for my x-intercepts here. Positive leading coefficient and behavior Q1 to Q3. So I know I'm going to try and do this smoothly, but it's like being on a skating rink. Okay, yeah, there we go. Not so bad. Okay, so this is the sketch of my combined difference function, and I want to know when, let me just get a different color again here. I want to know when f of x is greater than g of x, and so in order for f of x to be greater than g of x, that would mean that f of x minus g of x would be greater than 0, just moving g of x to the left side of the inequality. So all I need to do is look at my difference function here and find the intervals where that function is greater than 0, so above the x-axis. And so that gives me, again, the same intervals as before. Negative x is an element of negative 10 to 0, union 1 to infinity. And f of x would be less than g of x, where f of x minus g of x is less than 0, which means below the x-axis, and so the only interval where that occurs on this different function is 0 to 1. So I end up with the same solutions as before, and in this case it looks like this method is actually a little bit cleaner and easier than the first method. Don't have to do quite as much graphing, which is nice. Of course, you could also, if you can use technology, graph them both on technology, and that would obviously be the easiest way. But if not, then you would have to use one of these two methods. And so that is it for this sample problem. Thank you.